Hi everyone. Today we're going to talk about separation of variables. Separation of variables refers to a method that we can use to solve differential equations. We've solved differential equations before by integrating. This is going to let us solve a little bit more complex of differential equations. Take a moment to find the general solution to the differential equation shown. Hopefully what you did is you recognized the general solution to the differential equation is going to be the antiderivative. Hopefully you remember that from chapter 4. Antiderivative of x is x cubed over 3. Antiderivative is e to the x is e to the x. And then, of course, we need our constant of integration at the end. Believe it or not, we've actually been using separation of variables without even knowing it to be able to do this. So we've been able to find the antiderivative without much thought, but really what's happening here is we're really multiplying both sides of the equation here by dx. And then taking the antiderivative of both sides. This is exactly what we did, we just really didn't have the notation associated with it. But now, as you can see, the integral of dy is just y, and then the integral of x squared plus e to the x is exactly what we came up with in that previous slide. So we haven't needed to use separation of variables yet, but like I said, this will let us be able to find the general solution and particular solutions to more complex differential equations. The steps to solve differential equations through separation of variables: we need to make sure we rearrange the equation so that everything with an x and everything with a y are on opposite sides of the equations. This includes dx and dy. Dx counts as a variable with dx, and dy counts as a variable with dy. It's important to note here that you cannot have dx or dy in the denominator on either side of the equation, because we do not know how to integrate something, for example, like the integral of x over dx. We don't know how to do that. So we need to make sure dy and dx are on opposite sides of the equation and not in the denominator. Let's go through an example together. First thing we want to do is get all the x's on one side and all the y's on the other. So I'm going to start by subtracting x squared from both sides. And then I'll multiply both sides by dx. And we don't have to divide by 3 at this point. However, I'd like to, because eventually, if we can, we're going to try and solve explicitly for y, so might as well get it as close to y being by itself at this point in time as possible. All right, now it's time to find the integral of each side. Integral of y is y squared over 2. Integral of negative x squared over 3 becomes negative x cubed over 9. And I'm going to call this constant 1, constant 2. I can move this constant over here by subtracting it, but a constant minus a constant is still a constant. So I actually just need 1 plus c, and usually we keep it on the side of the equation with the x's, because we're going to solve explicitly for y. So we can multiply both sides by 2. And again, 2 times a constant is a constant, so we're just going to leave it like that. And then we can solve explicitly for y. It's not very pretty, but we end up with y is the square root of negative 2x cubed over 9 plus c. So this is the general solution to this differential equation. Let's do an example where we're going to find the particular solution to the differential equation. So if you remember, particular solutions mean that we're still going to have to find the antiderivative. but we have this initial condition that we're working with here that's going to actually let us solve for that constant of integration. So let's go ahead and do it the same way we were before. Going to get everything with y on one side, everything with with x on the other. So we can divide both sides by y minus 1, and we can multiply both sides by dx. And then we're going to integrate. Integral of dy over y minus 1 is going to be ln of y minus 1. Integral of x squared is x cubed over 3. Okay. So we want to solve for y, so I'm going to raise e to both sides of the equation. And that lets us actually cancel out this ln, e to the ln kind of cancels out, so we're just left with this y minus 1. Now, this is where it gets a little tricky, so we're I'm gonna actually move over here so I have more room. We're going to add 1 to both sides of the equation. That's not the tricky part. What the tricky part here is this plus c in the exponent. So if you remember, if I have x to the a times x to the b, that's the same as x to the a plus b. And I can kind of go backwards too. X to the a plus b is x to the a times x to the b. So this e to the x cubed over 3 plus c is the same as e to the x cubed over 3 times e to the c. But e to the c, that's just a constant itself, because e raised to any constant is still going to be a constant. So I can rewrite this as y equals a constant times e to the x cubed over 3 plus 1. And then I have this initial condition when x equals 0, y equals 3. So this has to be 3 equals c e to the 0 plus 1. E to the 0 is just 1, so that means c has to equal 2. So my particular solution here, I'm running out of room. My particular solution here is y equals 2e to the x cubed over 3 plus 1. So you just have to be careful. Whenever you end up with like a plus c in the exponent, you're going to want to bring it down in this way and turn it into a constant. So that's really the only like tricky part of this particular problem. Let's do one more example in the form of a word problem, and this one actually might look kind of similar to something we did in the exponential growth and decay section. So here we have the rate of change of the number of coyotes, n, is directly proportional to 650 minus nt. So you might remember when we talked about exponential growth and decay, that means that when the rate of change is directly proportional to a function, we're talking about exponential growth and decay, but we never really talked about why. So I kind of want to show you how to get from the answer to this question using separation of variables. So if something is directly proportionate to something else, that means that the rate of change of n, so that means dn dt, equals some constant times this function. And I'm just going to leave it as n. That's what directly proportional means. So we can find this function, and this actually turns out being a particular solution problem using separation of variables. So I'm going to divide both sides by 650 minus n and multiply both sides by dt. I do want to warn you, this is a bit of a lengthy problem, so make sure you're pausing and taking notes as we go, so you're making sure you're understanding the steps. So divide both sides by 650 minus n and multiply both sides by dt. And then we can integrate. So over here, we're going to need some u substitution. Du is going to be negative n. We have the, or excuse me, it's going to be negative 1 dn, sorry. So we have the negative, we get it there by multiplying and dividing by it. And then integral of k dt is just kt. This becomes ln of, negative ln, excuse me, of 650 minus n, because we have a du over u situation. Bring this over here so I get more room. And I'm actually going to multiply both sides by negative 1. But 650, or excuse me, I'm sorry, negative 1 times a constant is still a constant, so I'm just going to leave that as plus c. And then raise e to both sides of the equation. The e and the ln cancel out. And like the previous example, this e to the negative kt plus c becomes c e to the kt. We can add n to both sides and subtract c e to the kt from both sides. So we now have n equals 650 minus, oops, excuse me, that's a negative, minus c e to the negative kt. So we have when the population is 300 times t equals 0. So that means the number of coyotes we're dealing with, we got 300 coyotes at time t equals 0. But then e to the 0 is just 1, so c has to be 350. So I now have n equals 650 minus 350 e to the negative kt. So I just need to find k to be able to answer the question of what the population is at time t equals 3. So I can use this second point here. When time t equals 2, the population has increased to 500. So I have 500 coyotes when t is 2. So now I'll subtract 650 from both sides. Divide both sides by negative 350. Take the ln of both sides and divide both sides by negative 2. And that's going to leave me with k is approximately 0.424. So now I have our full number of coyotes function. And I can use that to figure out, well, how many coyotes are there at when t equals 3. So I just need to find n of 3. And when I do that, I end up with 420.87, but we're talking about coyotes, so let's say we have got 421 coyotes, because we do not have 0.87 coyotes, or at least I really hope not. This is kind of interesting, because what happened here was we started at 300 coyotes, we went up to 500, and we dipped back down. So even though we are following an exponential um, model here, it's not a straight up. It's actually doing this kind of a thing, which is actually going to be a lot closer to what a population in general would look like, because you can't logistically have a population that just increases exponentially. Eventually, you're going to run out of resources. So this coyote model is probably closer to something you would actually see in nature.